So now we're going to talk about pressure. So pressure is the amount of force exerted on a given surface area. So you can calculate pressure as force over area. So if you notice, this is incredibly similar to your density formula, where it was density is mass over volume. So now it's pressure equals force over area. Okay, so it's the same kind of formula where you've got the three different variables and then one variable equals the other two, one on top of the other. Okay, so pressure is measured in units of pascals. So pascals are defined as a Newton over meter squared. So newtons are the unit of force, and then area, of course, is measured in meters squared. Okay, but it's shortened to Pascal, one to honor famous scientist Pascal, Blaise Pascal, who did a lot of work on pressure, and then also two to just kind of make it a little bit easier to, say the units. Okay, so the Newton is the SI-derived unit of force. And then getting into buoyant force. So buoyant force, this is obviously going to deal with fluids. So fluids are anything that flows. So it's either a gas or a liquid. Okay, so we don't necessarily think about gases being fluids, but they are. Okay, so with buoyant force, this goes into the Archimedes principle. So the Archimedes principle states that the buoyant force of on an object in a fluid is an upward force, and it's equal to the weight of the fluid that the object displaces. Okay, so in this case here we can see the object is lowered into a container of water, and then once that object is completely submerged, the weight of the displaced fluid equals the buoyant force acting on the object. Okay, now in this case we'll go into that in just a second about like the weight versus the buoyant force and so on. Okay, so using the buoyant force, you can actually determine if an object is going to float or if it will sink. So we're going to use this image here. Okay, so first up, we're going to talk about the seagull. So the seagull, the buoyant force of the water is actually greater than the weight of the seagull. So the buoyant force acting on the seagull is equal to the weight of the displaced fluid. Okay, so you notice that it doesn't actually displace a whole lot of fluid, but it's because there isn't a whole lot of weight on the top. Okay, so it's actually displacing more weight in the water than it actually weighs. Okay, like the top of it weighs, which is why it floats. Okay, so you have a greater force pushing up than you do of the weight of the bird pushing down, which is why it floats. Okay. Now, if we talk about the shell, okay, so the buoyant force on the shell is actually less than the weight of the shell itself. So the weight of the shell is greater than the buoyant force. So it's a greater force pushing down than it is pushing up, meaning that this will sink. Now with the fish, okay, the fish is actually kind of different because its buoyant force equals the weight of the fish. So the buoyant force equals the fish's weight, so the fish is suspended in the water. Okay, so it doesn't really float, it doesn't really sink, but it can swim through the water. Okay, so it's suspended in the water. Now an object will float or sink based on its density. Okay, so if the object is denser than water, it will sink. Now if the object is less dense than water, it will float. So if you think about a ship, because this was always a question that I had growing up, okay, how does a ship float? And it's really based on kind of the structure of the ship itself. So of course, if we see a block of steel, okay, a block of steel is denser than water, so the block will sink. Okay, now shaping that block of steel into a hollow form increases the volume that that block of steel occupies. Basically adds in gas, which is a lot less dense than water. Okay, so because you're increasing the volume but keeping the same mass, it means that your density decreases. And because your density decreases, you can actually decrease it to a point where it's less than water. Okay, which, because you have now created an object that is less dense than water, it will float. Sorry, didn't mean to go on there yet. Okay, so that's how you can actually make a ship, and why ships are generally shaped in such a specific way. Okay, why you generally have this big hollow portion in the bottom of the ship. Okay, so even if you have, like, say, a living area in this portion of the ship, you still have a lot of gas that's in that area, which decreases the density of the ship itself. It's also still got that increased volume, no matter what you put inside that living area. Okay, so it's still going to float, right? Now, if you were to hit an iceberg, say, and puncture a hole in the hull of the ship, sorry, that would actually allow water to flow into the ship, decreasing that volume that's above water, okay? And so it would also increase the mass, which would then throw the density out of whack, and then the density would increase until it's greater than the density of water, and that's why your ship would sink. Okay? Okay. So, Pascal's principle. This relates to, pressure in fluids. So a change in pressure at any point in an enclosed fluid will be transmitted equally to all parts of the fluid. Now, this doesn't really seem all that useful until you start talking about hydraulics and pistons and things like that. Okay, so if the pressure in a container is increased at any point, the pressure increases at all points by that same amount. Okay, so we use this a lot in hydraulics. Basically, you can put a small amount of force into a small area on this fluid, and then that force will get translated all the way throughout the fluid, okay? Because it's increased at any point, or all points in that fluid by the same amount. But then if you have an increased area, okay, having that force translated along there, that pressure translated along there, if you have an increased area, you also need to have an increased force. Okay, so just applying that pressure can actually cause an increase in the force on the other end. Okay, now this is kind of confusing, but so in hydraulic devices, so you have the pressure on the left side over here is equal to the pressure on the right side over here. Okay, so P1 equals P2. Now, if you have pressure equals force divided by area, okay, you can also set it up as F1 divided by A1 equals F2 divided by A2. Okay, now say your second area over here is twice as large as the first area here. Okay, now in order to keep this proportion the same, that means that your force has to be double on the right, okay, in order to keep that proportion between the force and the area the same, right? So you've got a small area and a small force on the left, and that translates to a large area and a large force on the right. Okay. So fluids in motion. This is also kind of a strange thing to think about. Fluids move faster through small areas. Okay, so they move faster through smaller areas than they do through large areas. Okay, so if you've ever been on like, kind of like a lazy river sort of thing, but it's actually got some speed to it. Okay, so if you go through a smaller area, a narrower area, your speed tends to pick up. Okay, so if you can remember that, this kind of helps you think through this. All right, so think of also placing your finger over part of the end of a garden hose. Okay, you decrease the area, but the same amount of fluid has to come out of that area in the same amount of time, okay? Because there is still the fluid backup throughout the rest of the garden hose, okay? So if you have, say, 1 kilogram of water coming out of the end of the garden hose in, say, a second, and I know that's a great garden hose, but if you decrease that area, you still have all of the water behind it trying to push through at that same rate, okay? So where you're still getting 1 kilogram out through a specific area of the garden hose in 1 second, right? So it has to be going somewhere. So if you decrease that area, it means that the fluid has to go faster to keep up with the rest of the water pushing it out. Okay, so the force will stay the same even though the area decreases, which makes the pressure increase. And if you have higher pressure, it comes out a lot faster. Okay. And then one final thing to talk about with fluids, we also talk about the viscosity. So viscosity of a fluid is basically a liquid's resistance to flow. So if you think about water, it has a pretty low viscosity, which means it doesn't really resist flowing, right? It'll move pretty quickly, pretty easily. But if you have a high viscosity, it means that it kind of resists moving, right? So if you try to drop it off a spoon, okay, so if you had, a bowl of water, and you take a spoon and you pick up some of the water with it, and then try to just tip the spoon over and let it run off the spoon, water is going to flow really quickly, really easily. But now think about if you had a bowl of honey and you did the same thing. The honey is going to resist coming off of that spoon. So it has a high viscosity, doesn't really want to flow. Okay, so honey has a high viscosity, water has a low viscosity. So when you talk about viscous or viscosity, viscous liquids, oftentimes I always tend to think about molasses. There was actually a molasses disaster, which I know sounds really weird, in Boston in the early 1900s. It's just kind of one of those weird quirks of history that I don't think a lot of people often talk about or most people know about. But it's kind of an interesting story. I posted a video about that, so it goes into more detail and actually shows you some pictures from that. But viscosity isn't really something to kind of joke or laugh at, basically, if something's very viscous. And if you've ever heard that term, you're slower than molasses, yeah, molasses can move when it needs to. It's viscous, so it doesn't want to move all that much, but if you get enough pressure behind it, enough force behind it, yeah, it's going to move. And that's really what they saw with this disaster. I think it got up to speeds of 35 miles an hour or something. So it was kind of ridiculous, but I'll leave the rest of that for that video. Okay, so that is it for this section.